Hi, welcome to Algebra 2 Common Core. Today we're going to be working with vertical dilations, in which we're going to be stretching or compressing functions. This is lesson number 3. So we want to create a table of values for the function f of x, starting with an x value of -1 and going all the way to an x value of 5. Now, if you go to your graphing calculator, you can enter f of x in your y1 and then go to your table start and make that begin with -1. Look at the table, and I see that I have y values of 8, 3, 0, -1, 0, 3, and 8. Example number 1 begins with the function f of x equals x squared minus 4x plus 3. We'd like to create a table of values for this function from -1 to 5. Now, this of course can be done using your graphing calculator, or you can do it by mentally computing the values. I'm going to have to go back and forth between the previous page because unfortunately the tables were posted on the previous page. So I'm going to graph those points on my axes. So take a few minutes to graph and then come back and see if your graph matches mine. Check your graph with mine and see that the parabolas match. I have x-intercepts at 1 and 3 and a y-intercept at 3 as well. Now we'd like to, in part B, determine an equation for g of x, and g of x is defined as 2 times f of x. We're going to need to create a new table of values and then graph g of x. So let's algebraically find the equation first of all. So g of x would be equal to 2 times the function f of x, so 2 times x squared minus 4x plus 3. When I multiply each term by 2, I'm getting the new function 2x squared minus 8x plus 6. So I now want to create a table of values for this one. Now again, I've provided room in your notes for you to give that table of values for g of x. I'm going to go on my graphing calculator and create the table for this new function 2x squared minus 8x plus 6. When I do that, the x-coordinate stays the same as -1, and the y-coordinate is 16. But that's clearly too big for my graph, so I'll go to the next point. When x is 0, I end up getting an answer of 6. So at 0, the y-intercept is 6. That, of course, makes sense because all we've done is doubled our y value. At 1, the y value is 0. At 2, the y value is -2. At 3, I'm back at 0 again. And at 4, it's also 6. So connecting these points, I see that my red graph is going to be the graph of g of x. And I can see by looking at this that my graph has been stretched in the vertical direction. Notice that the horizontal direction, while it looks like the parabola is a little bit skinnier, the x-coordinates did not change. The y-coordinates were the only ones that changed. Let's go ahead and try part C, where it says let's find the equation for h of x, which is 1/2 f of x. So algebraically, let's make our equation first of all. H of x is equal to 1/2 times the function f of x, x squared minus 4x plus 3. So that gives me the new equation, 1/2 x squared minus 2x plus 3/2. Now again, pause the video for a minute and enter this function in your y equals. You could also enter your original function as y1, g of x as y2, and h of x as y3 so that you can see all three of them graphed at the same time. This would be especially effective if you've got a color graphing calculator and you can see the three different colors on the graphs. So go ahead and pause the video and make the table of values for h of x. When you come back, we'll plot those points. So for h of x, I've got the ordered pair -1, 4, right here, 0, 1 1/2, 1, 0, 2, -1/2, 3, 0, 4, 1 1/2, and 5, 4. So you'll notice that all three graphs have exactly the same x-intercepts, but all of the other points have changed. In the case of the blue graph, each y-coordinate is half as much as the graph of f of x. So let's go ahead and write down this information. Given the graph of a function f of x and a constant value k, if k is a number that's bigger than 1, then when we multiply the function f of x times k, we end up vertically dilating the graph. But when k is bigger than 1, that means that my graph will be stretched. So I'm going to put that in parentheses. It's a vertical stretch of the function f of x. If, however, k is a fraction that falls between 0 and 1, then when I multiply f of x times k, it's going to vertically dilate. We say the same words, but the dilation will actually not be a stretch, it will be a compression. So it compresses f of x. In both cases, what we are doing is multiplying the y value by k. So please write that in the box in your note packet. And think about what happens when we multiply by a k value bigger than 1 and a k value smaller than 1. Let's try exercise number 2. It says the quadratic function f of x has a turning point at -4, 10. Of course, we know that a turning point means the vertex. We're going to do some transformations to this parabola. So the quadratic y equals 1/2 f of x minus 3 would have a turning point at what point? So let's think about what the different transformations are. Taking the first transformation, we see that we are multiplying our f of x by 1/2. So the 1/2 f of x really is just a vertical dilation by 1/2. That means that we're taking our y value and we're multiplying every y value times 1/2. So in the case of the turning point that we were given, -4, 10 is going to become the point -4, 5. Only the y-coordinate is multiplied by 1/2. Now the second transformation that happens is that we have a translation or a shift. The translation is down because we see that we are subtracting 3. So it's going to be a translation down of 3. That means that we're going to take this new point -4, 5 and we're going to move it down by 3 by subtracting 3 from the y-coordinate. So it's going to become the new point -4, 2. So here is our new turning point for our transformed graph. In exercise number 3, we have just a random point on our graph, -3, 12. It lies on a function f of x, and we want to know what would happen to this point if we take the graph y equals 3f of x. So of course 3f of x means that we are just taking our y value and we are multiplying by 3. So the point negative 3, 12, when I multiply the y coordinate by 3, will now become the point negative 3, 36. So choice number 2 is our answer because I'm only doing one transformation to that original point. In example number 4, we have another quadratic function g of x. So this is another parabola. This parabola has a y-intercept of 12, so that means that we're starting with the point where x is 0, y is 12. So 0, 12. The transformation for h of x this time, our first step is going to be multiplying the g of x, or the y coordinate, by 3. So that means that we're taking the point 0, 12 and multiplying the y value by 3, so that's going to give us the new point 0, 36. For step number 2, because we are doing the subtract 5, that means that we're going to translate this point down 5 units. So our y coordinate will subtract 5. So our point 0, 36 will become the point 0, 31. So that tells me that our new graph has a y-intercept of 31, and we'll pick choice number 4. In example number 5, we're starting with the given graph y equals f of x. Notice that this one doesn't have an equation to begin, it's just a combination of line segments. We're going to focus on the endpoints of those line segments. We want to consider the new function g of x, where g of x is defined as 2f of x minus 3. So the question first is, what two transformations have occurred to the graph of f of x to produce the graph of g of x? We always start with the multiply, so our first transformation is going to be a vertical dilation of 2. So for every point, we're going to have to multiply the y coordinate times 2. Our second transformation is going to be the subtract 3. So that means that we are going to translate each and every point down 3 units. So we're going to take our y coordinate and we're going to subtract 3 to get our new point. So in order to graph g of x, let's start with the endpoints for f of x. So looking carefully, I see that I have a point over here, and the coordinates of that point are -6, -2. The next point that I'm going to look at is this one right here, and that has coordinates -3, 2. The next point would be this one right here with coordinates 2, 1. And the last point would be this endpoint right here with coordinates 5, 5. So I'm going to do the two transformations to that table. So for the first transformation, let's just do the dilation of 2. So we're going to multiply 2 times f of x. Keeping the x coordinate the same, I've got -6, -4, -3, 4, 2, 2, 5, 10. Now let's go ahead and do the second transformation to all of those points. So we're going to take our x value and keep that column exactly the same. And our y column in this table will have to subtract 3. So -4 minus 3 would be -7. 4 minus 3 would be 1. 2 minus 3 is -1. 10 minus 3 is 7. So this is the table of values for our new function g of x. I'm going to change colors and plot each of those points. So -6, -7 puts me right here. The next one, -3, 1, would be this point right here. 2, -1 would go to here. And 5, 7 would come up here. So connecting these endpoints, the blue graph is now the graph for g of x. Notice that we had to do each of those points individually in order to get the graph of our transformation. Let's try the last two examples. For exercise 6, the function h of x has a range given by the interval from 2 to 10. So the function f of x is defined by f of x is equal to 3/2 times h of x plus 8. So we want to know what range is there going to be for the function f of x, which is our transformed function. So I'm going to take each of the y coordinates, or the range values, and I'm going to start with the number 2, and I'm going to say, okay, we want to first of all multiply by 3/2. So I'm taking the y value and multiplying by 3/2, and that's giving us a new y value of 3. But then we will do the transformation where we add 8 to the y value, so that's giving me a new y value of 11. Let's do the same thing to the other endpoint of the interval, 10. So multiplying by 3/2, that's giving me a new y value of 15. Adding on 8, that's giving us a new value of 23. So our new range is going to be the values from 11 to 23. So that's going to be choice number 1. In example number 7, we're given the graph of a quadratic function, and we're told that this graph is a transformation of the function y equals x squared. We are also specifically told that we have a vertical stretch and a vertical shift. So our question is, what is the stretch, what is the shift, and then using that information, can we make the equation for the function? Well, the important thing to start with is our original function, y equals x squared. So I'm going to graph that in red on my graph. So go ahead and do that with me. Y equals x squared would have a vertex at 0, 0. It would go through the point 1, 1, but also through the point -1, 1. It would go through the point 2, 4, but also the point -2, 4. So my function, y equals x squared, looks like this graph right here. And I want to know what has happened to each point in order to make the new black graph that I'm given. So the easiest one to look at would be the point 0, 0. 0, 0 became the point 0, -7. Well, in order to become the point 0, -7, it doesn't matter what I'm multiplying by because I'm multiplying 0 and that stays 0. But I can clearly see that this is going to be a shift down 7 units. So the shift is going to be a translation down 7. That's going to help us quite a bit because now I can look at other points to determine what my vertical stretch is going to be. Specifically, let's start with the point 1, 1. The y coordinate is 1. So whatever I do, I'm stretching it and then I'm moving it down 7. So the question is, where does it have to move to after the stretch so that when I move down 7, it lands here? So I'm just going to count up 7 from this point, and I see that I'm going to get this point right here. That point is at 1, 2. So when I take that blue point and I shift it down 7, I'm ending up at my new transformation graph. Well, clearly that means that I'm going from the point 1, 1 to the point 1, 2, and that tells me that my k value, my stretch, must be 2. So this is a vertical dilation of 2. Now we can also check some of the other points to make sure that a vertical dilation of 2 makes sense. So for example, if I go to the point, this one right here at 2, 4, I want to land eventually at this point 2, 1. So if I stretch the point 2, 4, let's try that one, 2, 4, if I stretch it by 2, it becomes 2, 8. And then if I take that point and I go down 7, that's going to give me the new point 2, 1. Did I end up at that new point 2, 1? Yes, that's right there. So I know that I must have a vertical dilation of 2 and a translation down of 7. What does that equate to in my equation? Y equals the x squared is being multiplied by 2, and then that answer I can subtract 7. Now we can always check our answer by entering this into my graphing calculator, y equals 2x squared minus 7, and be sure that you get the graph that we were given to begin with. Thanks very much for listening today. We'll work some more on vertical dilations tomorrow in class. Have a great night.